Hey everybody, my name is Calvin, and welcome to episode 1 of my Python 101 course. Python is one of the most widely used programming languages because it's readable, flexible, and it shows up pretty much everywhere from automation scripts to web backends to data work and machine learning. More importantly for beginners, it's a solid language for learning the core ideas that show up in pretty much every single programming language that exists. If you understand those fundamentals in Python, you can transfer them to other languages later without having to start over. The goal of this course is to take you from complete zero to being able to write real programs on your own. That means you won't just follow along and copy code. The goal here will be to understand what each line does, know how to write tests, and learn how to debug when something doesn't work. I'm also aiming to build good habits early, like organizing code into projects, using an editor properly, and keeping your work saved and versioned. By the end, you should be comfortable reading and writing Python, solving common beginner to intermediate level elite code problems, and starting small projects without feeling lost. For the first video, we're just going to be setting up the environment that we'll use for the entire series. We're going to install Python, install a code editor, in this case VS Code, set up any key extensions, set up Git and GitHub, so all of our coursework lives in one course repository. Without further ado, let's get started. The first step here that we have to do is to install Python. Go onto Google and search Python download, and use the official python.org download page. Should look something like this. Click on it. Then, we want to download the latest version for our operating system. In my case, I'll be using Windows, but if you're following along with a different OS, the process should be very similar. Scroll down to the latest Python release, in this case Python 3.14.2, and then click download. Scroll all the way down to files, click on Windows Installer. An executable will be downloaded. We can click on it. In our setup window here, we want to click the checkbox that says add python.exe to path. Path is a list of locations your terminal searches for commands. So if Python isn't on path, typing Python in the terminal won't work, and tools like VS Code won't be able to automatically find it reliably. Checking that box prevents the most common setup issue. Then, run the installer using the default options. I already have Python on my machine, but follow along with the instructions for your specific installation. Let's test the Python installation. For Windows, we open up Command Prompt, or on Mac, open up Terminal, and type in Python -- version. This should give you your installation of Python and the specific version. In my case, I'm using an older version of Python 3.12, but that should differ on your machine since you just downloaded something like 3.14.2. If that doesn't work, try Python 3 instead of Python. Then let's run a quick test. Type in Python or Python 3. Something like this should pop up. Now type in print hello world, exactly like that, and then hit enter. If hello world is successfully printed, then that means your Python installation is up and running. Next, we'll need an editor. You can technically write Python in anything, even Notepad if you wanted to, but VS Code makes learning and debugging way easier. Go to Google again and search up VS Code install. Navigate to the official Visual Studio Code site. Follow the instructions for your specific OS and download it like any other app. The reason we'll use VS Code in this series is because it supports running code, debugging with breakpoints, autocomplete, and project organization, which are all things that you'll need if you want to program beyond any tiny scripts. Open up your newly installed app, and it should look something like this. Now, we want to download the relevant extensions. I already have a few downloaded, but I'll point out the ones that you'll need. First, download Python by Microsoft right here. Install Pylance by Microsoft as well. This will improve autocomplete and any error checking. And finally, let's also install Jupyter. You can disregard this for now, but we'll be using Jupyter notebooks later for any explanations and experiments. Now, we want to install something called Git. Git is what tracks our changes locally. On Mac, Git is usually already available. On Windows, we can download Git for Windows from the official site and install it. So like usual, search up git install, navigate to your specific OS, and follow the instructions. During installation, any defaults are fine for this course. Now, let's go back to the command prompt. Like our Python command up here, we want to confirm that Git works as well. Type in git -- version, and if something pops up like this, then you're good. Now, we'll need a GitHub account. Go on Google and navigate to github.com, and a page like this will show up. We want to create an account if you don't already have one. Click sign up. Type in an email that you'll keep. Put in a password. Type in a username that you're comfortable putting on projects, since this will be a part of your public portfolio, and hit create account. I already have an account, so I'll just simply sign into my own. You'll be brought to a page that looks like this. We want to create a course repository on GitHub. Navigate to create new right here. Click on the drop-down menu, click new repository. From here, choose yourself as an owner. Type in your repository name. In this case, I'll call it course repository. We can make our repository public if you want to share it or use it as a portfolio. We can make it private if you prefer, but public is fine for the course code. Don't touch template. Let's add a README, which creates a main page for your repository so it's not empty. We can optionally add a git ignore. We can also optionally add a license, but don't worry about that right now. Click create repository. Now we've created our course repository. We're ready to get actually coding. Now we want to create something called a clone of our repository onto our computer. Cloning means downloading the repository to your computer with Git, so VS Code can open it like a normal folder, and so Git can track our changes as we work. Navigate to VS Code. Navigate to a new window on VS Code. Click clone Git repository. Take the URL of the repository that we just made. Make sure that this is your username and the course repository and nothing else, otherwise it won't work. Hit enter and clone it somewhere that you won't lose it. In our VS Code, now we want to navigate to the folder that we just cloned. You can do that with open folder, navigate to the folder that you just created, and something like this will pop up. From now on, this folder is where we do everything. When we write code, we will write it inside this exact repository. When we finish a lesson, we commit and push changes so your GitHub stays updated. Now, we want to make sure VS Code is using the correct Python interpreter. Open the command palette under the View tab and type in Python select interpreter. From here, we want to pick the Python version that matches what we saw in our terminal earlier. In this case, it was 3.12.0 for my specific computer. This matters because some systems have multiple Python versions and you want VS Code to run the same Python that we installed. Now, inside the repository folder, create a file called hello.py. Navigate to new file right here, type in hello.py, and this will create a Python file for you. Type in print hello from Python. Save it using Control S. We can run our hello.py using the run command up here, which should give us something like hello from Python right down here. Optionally, from the course repository directory, we can also run python hello.py, which should give us the exact same thing. Now, we want to save this work to GitHub. I'll be showing you the full Git workflow that we'll be using constantly, so we're going to keep it simple and repeatable. First, let's check what changed. Type in git status. You should see hello.py listed as an untracked file right here. Now, we want to do something called staging the file. Staging basically means I want this change included in the next commit. Type in git add hello.py, which will add hello.py to the staging area. Type in enter. Now, we'll be running a commit command. A commit is a saved snapshot of your code at a point in time. Type in git commit. And this will be our commit message. For a commit message, we don't want to just type in gibberish. Our commit message should be descriptive, yet simple. In this case, add hello.py will suffice. Hit enter. If our commit was successful, we should see something like this. Now type in git push. And if a message shows up that looks something like this, then it's successfully been pushed to the repository. The first time you push, Git might ask you to sign in, which is normal. On GitHub, the recommended approach is using a personal access token instead of your password if prompted. If you get that prompt, you want to log into GitHub, generate a token, and paste it when Git asks for a password. Now, navigate to your Python course repository on GitHub. You should see a hello.py now, along with your commit message. Now, we've successfully set up our repository. We now have a local copy on our computer and a remote copy on GitHub. Anytime you make changes to the repository, you'll use the same three commands: git add, git commit, and git push. If you ever need to get the latest version from GitHub onto your computer, we can also use the git pull command. And that's our setup. We now have Python, VS Code, Git, and a GitHub course repository. From now on, every lesson will be inside this repository, and at the end of each video, we'll commit and push so your progress is saved and easy to review. In the next video, we'll start programming with variables, types, printing, and input. Thanks for watching, and I'll see you guys in the next video. Hey everybody, my name is Kelvin, and welcome back to episode 2 of my Learn Python series. Today, we're going to be introducing variables and data types. If you haven't watched episode 1, the episode is linked in the top right. Before continuing on this video, variables are how your program stores information. If you want your code to remember something, reuse it later, or update it over time, we can put that value in a variable. A variable is simply a name that points to a value. To set a variable in Python, we use assignment. You write a name, then an equal sign, then a value. For example, we can assign a variable called age equal to 21, just like so. The equal sign basically means store this value under this name. It's not an equation, but it's an instruction to Python. Moving on to data types. A data type is the category of a value. Python needs to know the type because different kinds of values are stored differently in the backend and behave differently. Even if you don't think about types yet, Python always does. The most important beginner data types are these. An integer, or shortened to int, is a whole number with no decimal point. Integers are used for storing things you count: number of messages, number of students, a person's age, quantity of items, a score, a year. If it makes sense to count it in whole numbers, we usually want an int. So our age variable that we just set is an integer. A float, just called a float, is a number with a decimal point. Floats are used for things like prices, measurements, averages, and anything that needs fractional values. Temperatures, distances, and money amounts often show up as floats. You'll see floats a lot whenever division is involved. Say, for example, we want to set age to a float. We can simply do that by creating into a fraction. This is a float data type. Our next data type is called a string, or shortened to str. This is text. Strings are used for names, sentences, labels, anything you will type as words, and also things like phone numbers or zip codes, because even though those look like numbers, you don't do math on them. If it's meant to be read or displayed as text, it should be a string. So for example, if we wanted to set age to a string data type, all we need to do is simply wrap it in double quotes. And this is a string data type of 21. The next data type that you must know is called a boolean, or just shortened to bool. It's a true or false value. Booleans are used for yes, no, or on, off states. Examples are variables called is logged in, has permission, is valid, or is student. Booleans become extremely important when we start writing conditional logic, because conditions are based on true or false values. So for example, say we have a variable called is old. We can set that to true, which is the true Boolean value, or we can set it to false. Now, our final data type is kind of a special case. None is a special value, which is just simply written as none. It represents basically no value or not set yet. You can use none when a variable exists, but you don't have a real value for it yet. For example, a user might not have provided a middle name, so you can store none. Or if you haven't calculated a result yet, so you start with none. For this example, we could interpret this as someone who hasn't been born yet. Someone who hasn't been born yet doesn't have an age. Python is a dynamically typed language. That means you do not declare the type ahead of time, like you would in C or something like that. You don't write, this variable is an int. Rather, you assign a value and Python automatically infers the type from the value. If you write age equals to 21, Python knows 21 is an int. If you write price is equal to $19.99, Python knows it's a float. If you write name is equal to a string value of Kelvin, Python knows it's a string. The type is attached to the value, and the variable name points to that value. Let's jump into some more concepts. Let's create a folder for this lesson, call it lesson 2, and open up a new file where we will store our first exercise. In this file, I want to touch a bit more on assignment. I'm going to type a few variables, print them, and then reassign one to show that variables can change. The key idea here is that the variable name isn't the value itself. Rather, it's a label, and you can point that label at a new value at any time. Say we had our age is equal to 21. Print statement right here. Age is equal to 22. Print age. Notice how we are using the same variable. I'll set this to my own name. And student is equal to true. And then we can, oops. And we can run this, and we'll see what happens. Get 21, 22, Kelvin, and true. We have to first understand what happened with age right here. We didn't edit the number 21. we reassign the name age to point to 22 instead. The reassignment idea is going to show up constantly later when we do counters, totals, and anything that changes as the program runs. Say if we got rid of this print statement right here, we set age to 21 right here, and then we repoint it to age 22, this would only print 22, since we got rid of this value right here. Save that file and move into a different file for our next concept. Let's touch some more on data types. In this file, I'm going to create one variable for each core type and then print the value and the type. The reason we're doing this is so you can recognize these types early, because a lot of beginner confusion comes from accidentally treating text like a number or treating a missing value like it's already set. Let's create a couple of variables. Count variable, price, message, is open, equal to false. Now we can create a couple print statements. So in this print statement right here, we're just going to print out count along with its data type. So you can see that count is 10 with the data type of integer. We can do the same thing for each one of these right here. We should expect to see 1999 with a float data type, hello with a string data type, is open with a Boolean data type, and value with a none type. If we run this, and we can see that that's exactly what we get. When we run this, we connect each type to the real use case. Count is an int because it's a whole number. Price is a float because it has decimals. Message is a string because it's text. Is open is a Boolean value because it's always going to be true or false. It's either open or it's not. Value is none because it represents no value yet. None is going to be useful later when we start writing programs where not everything has a value immediately. Moving on to our next concept. As I touched on before, Python is dynamically typed. Dynamic typing means Python decides the type based on what you assign. To show that clearly, I'm going to reuse the same variable name and assign different kinds of values to it. Again, the goal here isn't to encourage constantly changing types in real programs, as that's bad practice. It's to prove that Python doesn't require you to declare types up front, and that the type follows the value. So let's set a variable called x is equal to an integer 10. We'll print this with its type. Reassign it to 10 as a string. When you run this, the key takeaway is that Python is looking at the value on the right side of the equal sign and then deciding the type from that. The name x is just a variable name. It doesn't really have a fixed type built into it. So we can see that we can change x into multiple variable types. Our first 10 will print an integer, string, true, and none, corresponding with each of these print statements. Moving on to the next concept, variables make calculations readable. Here, I'm going to do a calculation with raw numbers first, then rewrite it with variables. Variables help with readability. Even if both versions work, the version with variables is easier to understand, easier to change, and easier to debug. Say we had a print value. Say we had a print statement of 8 times 60. Sure, we can print this and we would get 480, but in the context of the program, what would an 8 and a 60 mean here? We have no idea. We can do something else instead. We can do something better instead. We can set a variable hours to 8, minutes per hour, set it to 60, and then total minutes is equal to hours times the minutes per hour. And we can print total minutes. We can print this, and now this should make more sense. Both of these will give us 480, but this one makes more sense because it's human readable. We know that obviously hours, we have 8 hours, and we have 60 minutes per hour. And so total minutes here, so total minutes should be 480. And that makes more sense if someone else were to read our program. If we need to change hours, it's also pretty easy. We can do the same thing. Set hours equal to 10 instead. Reset minutes. Redo our equation right here. Reset minutes. And then we can see minutes right here. And now this should give us 10 times 60, which gives us 600 minutes. The next lesson I'd like to cover is that naming matters. The file is here because naming is not a style thing. It directly affects how easy it is to understand your own code later. I'm going to show the same calculation twice. The first version works but is unclear, but the second version works and explains itself. You can quickly see how this might get complicated. So set x is equal to 39.99. We can set this to 0.0625. Z is equal to x times y. And t is equal to x plus z. And now we can print, say we're interested in printing the variable t. We'll get around 42.49. But what does this mean? If you wrote this before and came back to it later, could you really remember what x, y, z, t means? Now, we could do the same thing, but with better variable names. Say we wanted to call this subtotal. Y is the tax rate. Now total tax is the subtotal times the tax rate. And the total is equal to subtotal plus the tax. And now we can print total. These lines make much more sense than these lines up here. If you come back later and need to modify the code, the second version tells you exactly what to change. But in the first version, we have no idea what's going on. This becomes more and more important as your programs get longer. Let's do some more practice. Say we wanted to have a city variable called Boston, temperature variable equal to 32.5 is raining is equal to false, favorite number is equal to 7, nickname, and we have no nickname. This makes a lot of sense. We'd want to represent Boston as a string, temperature as a float for maximum accuracy, is raining is either true or false, favorite number is 7, nickname, if you don't have a nickname, it should be none. We can run this. We've successfully set every single variable with the correct data type. If you can comfortably write a file like what I just did, you're building the right foundation. You know how to set a variable, you understand that values have types, and you can check what type something is when you're unsure. We're done with our coding portion for today. Like the Git workflow that we mentioned last time, we want to do something like git status, which will change what exactly happened from before. As a quick note, I moved hello.py into its own lesson here, so this is what that means. And we've created 2 new directories, lesson 1 and lesson 2. With everything in lesson 2. We'll do the git add command, git add period, we'll add everything that's changed. And then we'll commit that with a nice commit message. And we'll push that to the repository. There we go. That's it for this episode. If you're brand new, this is a bigger step than it sounds. This is the point where Python stops being random lines of code and starts becoming a tool that you can represent real information with. You now know how to create variables using assignment, and you know that a variable name is just a label that points to a value. You also know the core data types you're going to see constantly: int for whole numbers, float for decimals, string for text, booleans for true or false, and none for no value yet. The main Python idea behind all of this, Python is dynamically typed, so it infers the type automatically based on what you assign. The reason this matters is because everything we do here will depend on variables and data types. When we start writing conditional logic, the conditions will be based on booleans. When you start accepting input from users, the values will come as strings, and you'll need to recognize what type you have before you can use it the way you want. When we start writing loops, you'll be updating variables repeatedly as your program runs. When we start writing functions, you'll be passing variables in and getting new values out. This episode is basically the vocabulary you need before we can start writing programs that make decisions and respond to data. If you want to practice before moving on to the next video, here's what I do. Open a new practice file and add a few more variables that represent real things in your life, then print them and their types. Don't worry about doing anything advanced just yet. Just get comfortable with the idea that you can store information under a name and Python will track the type for you. Once that feels natural, you're ready to move on to the next episode. In the next episode, we'll be starting simple conditional logic. That's where we take variables and booleans and use them to make decisions, so your program can do different things depending on your data. Thanks for watching, and I'll see you guys in the next lecture. Hey everybody, my name is Calvin, and welcome back to episode 3 of my Learn Python series. Today's lecture will focus on conditionals. As always, the course repository can be found in the description. If you haven't had the chance to watch episodes 1 and 2, Be sure to watch those before tackling this one. Conditionals are how your program makes decisions. Without them, your code runs the same path every time. With conditionals, your program can react to the values in your variables and choose different paths. The structure we're learning is pretty much built around 3 key words: if, elif, and else. An if statement checks a condition. That condition must evaluate to a Boolean value, which, if we remember from our previous episode, is true or false. If it's true, Python runs the indented block underneath it. If it's false, Python skips that block. If you include an else, Python will run the else block when the if condition is false. If you include elif, Python will try the next condition in order until one is true or it reaches else. One important Python detail: indentation is how Python knows what code belongs inside the if block. The code under the if is indented. When the indentation ends, the conditional block ends. That's why consistent indentation matters in Python. We'll cover these fundamentals in the exercises in this episode. Without further ado, let's create a Lesson 3 folder. Lesson 3. And let's create our first Python exercise file for this episode, 3-1. In this file, I'd like to cover an exercise for your first if statement. The goal here is to make the true runs, false skips behavior obvious, like we covered before. Say we had age is equal to 17. We have an if statement that checks whether an age is greater than or equal to 18. If it is, it should print an error message that says something like, "You are an adult." Print this. When you run this file, we should only ever see this line print because of our age variable. Our age variable does not match the criteria that we've provided in this if statement, so it will never trigger this print statement. Because age greater than or equal to 18 is false, Python skips the indented block underneath. Now, we can change the value. Say we change age to 18. Now this conditional will evaluate to true, because age is indeed greater than or equal to 18. This is the core mental model for conditionals. Your code is branching based on true or false statements. Let's move on to the next exercise. In this exercise, I want to cover the else statement. Most decisions will have 2 outcomes. Else basically is how we can cover the otherwise. Say we had a variable called temperature. Is equal to 45. If temp is less than 32, we can print something. Oops. We can print a handy error message that says it is freezing. But if it isn't, we can print it is not freezing. When you run this file, it should make sense that the only line that is printed is this "it is not freezing" line down here. Because temp is not less than 32, we skip this else statement and we move on to the else statement right after it. We can see this in action. It is not freezing. Yet, if we change temperature to, say, 30, 30 is indeed less than 32. Instead of skipping this conditional, it'll go into the indented code underneath and run that. It is freezing. The takeaway here is that exactly one of these blocks will run, either the if block if the condition is true, or the else block if the condition is false. Moving on to the next exercise, I want to cover comparison operators. Comparison operators are what you use to create conditions. They produce booleans. Say we had a variable called a and a variable called b, and they were 10 and 3 respectively. For an equal to comparison, the way to write it is with two equal signs. And this means equal to. For not equal to, it is an exclamation mark plus an equal sign. And this will be your not equal to operator. Or this will be your not equal to comparison. Our greater than operator is simply this symbol right here, like you would see in math, and this is greater than the opposite. The opposite symbol works for less than. Now, if we wanted greater than or equal to, we have our greater than symbol and our equal to symbol, which just says greater than or equal to. And then you might have guessed by now, the less than or equal to is just like this. Let's walk through these. When you run this file, all these comparisons right here will produce Boolean values, meaning it'll produce us a value that is either true or false. So in this case, right, we have A is equal to 10, B is equal to 3. A is not equal to B, which is true. Greater than 10 is greater than 3, which is true. False. Greater than or equal to is true, since A is 10. And this should evaluate to false. We can confirm this by running our file. False, true, true, false, true, false. Exactly what we expected. A common beginner confusion here is mixing up equal and equal equal. If you have a single equal sign, that is an assignment. It sets a variable. A double equal equal is comparison, which checks equality. In an if statement, you use equal equal when you want to check, is this equal? So something like this. Would not work. This would not work and would give us an error. But if we added an extra one, this would work. And this should print us hello. Let's move on to our fourth exercise for this episode. In this exercise file, I want to cover Boolean operators, and, or, and not. Sometimes you need more than one requirement in a conditional. Boolean operators help us combine conditions. Say we had a variable called isMember, and we are a member. Purchase total, say we spent $120. Now, if we wanted to check a conditional, that is basically saying, if you are a member and you've purchased more than $100, then the condition triggers. This is what this is for. If is member and purchase total is greater than or equal to $100, print discount applies. Else, no discount. Oops. The AND Boolean operator here means both part must be true for the whole condition to be true. If either part is false, the discount won't apply. We can run this and confirm this. We are a member, and we've indeed purchased more than the defined threshold, so we should get discount applies when we run this. We can get discount applies. But if we negated either side of the Boolean operator, then it would go to the else statement, because this is an AND operator. Say we changed is member to false. Say we weren't a member. Now we are a member, but our purchase total has reached the threshold. That doesn't matter, because we need both conditions to be true. No discount. Same thing if we had true, but we spent less than threshold, no discount, or if both are false. Now, or means at least one part must be true. Say we had an is coupon is equal to false, and is VIP is equal to true. If we have a coupon, or we're a VIP, then the discount applies. Else, no discount. The OR operator makes it so either side of the conditional, only one condition or both needs to be evaluated true for it to trigger. So we don't have a coupon, but we are a VIP. This is false and this is true. But this will still trigger this conditional statement because one side is true. We run this and we can confirm discount applies. We can have both true, and this would also trigger. The only way we reach the else statement is if both conditions are false. No discount. Now let's cover the not operator. The not operator flips a Boolean. This is useful when a variable name already expresses a true or false state. Say we had an is locked variable is equal to false. And if not, it is locked. Print. You can open the door. Else, the door is locked. Here, the not of is locked becomes true when is locked is false. The idea is rather simple. The not operator simply reverses the truth value. So this is basically saying, if it isn't locked, you can open the door. Else, that must mean the door is locked. And if you run this, you can see that we've indeed triggered this conditional, even though this statement on its own, without the not operator, would go to the else statement. But since we have the not here, we basically reverse the false. The opposite's also true. Say we had is locked is equal to true, and if not true, then you can open the door. Else, the door is locked. In this scenario, we skip down to the else statement and trigger this code. The door is locked. Moving on to our next exercise, I want to cover elif chains. Elif lets you check multiple cases in order. Python goes top to bottom. The first true condition will win, and the rest are skipped. Say we had a score is equal to 82. If score is greater than or equal to 90, we want to award our student with a grade of A. If their score is an 80, greater than or equal to an 80, then we will award them with a B. Same thing for the letter grade C. And D. Our fallback here is an F. When you run this, it prints grade of B. The order here matters. If you put scores greater than equal to 60 first, then almost everything would match that early and you'd never reach the later cases. See, if we run this, we get to print B because first, it doesn't match this condition, so it jumps down to this elif statement right here, and it indeed triggers this, so we print a B. Since we've triggered this condition here, we're going to be skipping all the other options below. Now, if we had something like 60 up here, it is indeed greater than 60, and so it'll print an A here, and I'll skip everything else down here, rendering pretty much all this code useless, since it'll trigger this condition before it ever triggers anything else. That's why you want to be careful where you put if in your elifs. Now, if none of them match, then we fall down to our else statement right here. In this file, I want to cover nested conditionals. Nested if statements are just if statements inside other if statements. You use them when you have decisions that depend on earlier decisions. Say we had a variable called is logged in. We can set that to true for right now. And is an admin equal to false. If is logged in, then we print user is logged in. If the user is an admin, we want to display the admin panel. Else if this user isn't an admin, then we want to only show the regular dashboard. An else statement for a catch-all, redirect to the login page. When you run this, it prints that the user is logged in and shows the regular dashboard. If you set is logged in is equal to false, you'll see it skip the nested part entirely and go straight to redirect login. The important thing to notice about nesting is just about this specific structure. The inner decision only happens if the outer condition allows you to reach it. Basically, what I'm saying is that this code block right here will only ever run if this exterior if is true. Even this inner conditional, if is logged in is false, it'll never reach here, regardless if they're an admin or not. And we can run this, and we can confirm. And that brings us to the end of lecture 3. As usual, we're going to get status. There's a slight change here. You can ignore that. I don't want this intro. You can see that we've added a lesson 3 folder. let's add this. Lesson 3. Commit it with a message that says lecture 3 conditionals. And we'll push this. And that's the core of Python conditionals. You now know what a condition is, how if, elif, else control which code runs, how indentation defines blocks, how comparison operators create true and false values, and how Boolean operators combine multiple conditions. In the next episode, we'll build on this by introducing loops, which is basically how you repeat logic without having to copy and paste the same lines over and over. Thanks for watching, and I'll see you guys in the next episode. Hey everybody, my name is Calvin, and welcome back to episode 4 of my Learn Python series. Today, we'll be covering loops in Python. What are loops? Loops are how you repeat code without having to copy and paste the same lines over and over. So anytime you need to do something multiple times, go through some set of values, or keep running until some condition is met, you can use a loop. There are 2 core loop styles in Python that you'll see constantly as a beginner Pythoner: for loops and while loops. A for loop is used when you want to iterate over some sequence of values. A while loop is used when you want to keep looping as long as a condition stays true. Before we jump into the exercises, as always, the course repository will be linked in the description. I highly recommend watching the earlier episodes before this for the best learning experience. Let's jump into the exercises. Like before, we'll create a lesson 4 folder, and we'll keep all of our exercises in there. Create a file called for-1.py. In this file, I want to introduce us to range. Before we can use for loops comfortably, we need to understand the range function, because it's the most common beginner way to say, repeat something a certain number of times. The range function is not a loop by itself. Rather, it's a value that represents some sequence of integers. You can think of it as a generator of numbers. The for loop is what actually will step through that sequence one number at a time and runs your indented block for each number. The most common form is range with a single parameter. In the range function here, the 5 is the stop parameter. In this default form, it always starts at 0, it always counts up by 1, and it always stops before the stop value. So range 5 would produce exactly 5 numbers: 0, 1, 2, 3, and 4. Notice how the stop parameter here, 5, that we passed in, was not printed. That's because range will always start at 0 and count up. We do not include the stop in here. The easiest way to understand that is to print the values as they come out of the range. In this loop that I'm about to write, the only job of the for loop is to take the next number and store it into the variable I, then run the print line. So we initiate I right here, and we'll print it. You can see 0, 1, 2, 3, 4. That's because for every iteration in this for loop, I increases by 1, like in range. We're simply just printing out the numbers that range produces. Now, we can also add another parameter into the range function. This time, we can pass in a start and a stop. So it'll look something like this, with 1 being the start and 5 being the stop. We can write the for loop for this again. The difference between this range function and this range function right up here is that we're going to start at 1 and increment until just before the 5. So in this case, we should expect something like 1, 2, 3, and 4. And we can run this to confirm. I can see that's exactly what we expect. Comment that out so you can see 1, 2, 3, and 4. Another cool thing that we can do with range right here is we can add a third parameter, which is step. The step is literally how much the number changes each time. As before, our default was 1. We incremented by 1. We can put in a step parameter of 1, and it'll look exactly the same as the ranges before. However, if we passed in a step parameter of 2, then we would skip by 2 instead. If the step is 3, you jump by 3 as well. So say we had 1 and a 5, and we passed in a 2-step parameter. Let's see how this works. What should we expect here? We should expect something that looks like 1 and 3. Notice how we still start at 1, we go up to 3, but we don't ever want to hit the stop condition. So since this step can't go up by 2 without violating the stop, we only print 1 and 3. We can run this and confirm. Now if I change this to a 6, we could expect something like 1, 3, and 5. The big takeaway here is that range is just a clean way to generate loop numbers. The for loop is what will use those numbers. Let's jump into actual for loops now. In a different file, we'll create our first for loop. Our first for loop will use a loop the way that beginners will actually use it, to repeat some action a fixed number of times. For example, this loop will print a statement 5 times. The loop variable exists here, but it's never used. We just use the fact that the loop runs once per value. Remember, in range, we have 0, 1, 2, 3, and 4, which repeats 5 times. Now, I would also increment by that number because it's corresponding with whatever range number is in here, but that doesn't matter for us, since all we're doing in the indentation is printing hello. So all we should expect is hello printed 5 times. Now, let's use the loop variable so the output changes for us each time. The loop variable is what holds the current value for the current iteration like usual. So we can have a slight iteration of what we did before for demonstration purposes. Say we wanted to have something like attempt, and we wanted to print I instead. We should see attempt 0, 1, 2, 3, and 4. Now, a beginner misunderstanding is that range will start at 0 instead of 1. If we wanted it to start at 1, we would just simply add a 1. So now we can have attempt 1, 2, 3, 4, and 5 for human readability. Another key thing to note is that the variable here can be anything. It doesn't need to be I. It can be number, and could be X, Y, Z, number, whatever you want to call it. Hopefully this gave you a glimpse into what exactly loops are capable of. Let's jump into our third exercise. In here, I want to create a running total pattern. This is one of the most important loop patterns you'll learn pretty early on. You initialize a variable before the loop, update it inside the loop, then use it after the loop. We're going to compute a running total. Total will start at 0 because 0 is the correct starting point for addition. Then each iteration of the loop will add the current number into the total. So say I wanted to do something like for I in range 5, and I had total is equal to total plus I. Now, the total variable up here will increment by I every single time the loop is run. Now, also notice that for each iteration, I will change according to the range values. What should we expect here? We should expect to see a 10 in the total print statement. Why? Because we're doing something like 0 plus 1 plus 2 plus 3 plus 4. 1 plus 2 is 3, 3 plus 3 is 6, and then 6 plus 4 is 10. We can run this, and we'll see that we do indeed get 10. Moving on to the next exercise. I want to cover a loop with simple conditionals. Now, we can combine the loops with the if, elif, else statements that we covered in the lecture before. This is where loops become especially powerful. You could apply the same decision logic repeatedly to many values. In this example, we're taking each number and categorizing it into a low, medium, and high. Say we had a for loop for I in range of 10. Now we can have something like if I is less than 3, then we want to print is low. And let's say we also wanted the number in here. If I is less than 7, then we can print I is a medium number. Else print I is a high number. Now we should see something like 0 is low, 1 is low, 2 is low, and so on. 0 is low, 1 is low, 2 is low, 3 is medium, 4 is medium. Since I increments by 1 each time the loop is run, we evaluate these statements every time. We can kind of look at it like a mini decision process that happens 10 times. For each I, Python checks the conditions in order. The first condition that's true is the branch that runs. Then it moves on to the next iteration. Moving on to the next concept, I want to cover break and continue. These are loop control tools. They change the flow of a loop while it is running. Break means stop the loop entirely, and the loop ends immediately, and then execution continues after the loop. Say, for example, we had for I in range of 10, but we had a conditional in here that said we wanted it to stop when I is equal to 5. Break. We can print I. Now what would this print? It would print 0, 1, 2, 3, 4, and 5. Now once we reached I is equal to 5, it breaks out of this whole entire loop right here, and nothing else is printed. We can confirm this. I misspoke because the loop breaks out. Notice how the loop is broken before we ever print 5. So that's why it only goes up to 4. So really, this loop would produce 0, 1, 2, 3, and 4. Now, if we were to move the print statement up here, then my previous statement would have been correct. Now let's take a look at the continue. Continue means skip the rest of this iteration and go to the next iteration, and the loop does not end. It just skips what comes after continue for that one singular pass. So say, for example, we had pretty much the same example up here. Let's uncomment that. For I in range 10, say we were interested in replacing our break with a continue. And we again print the numbers right here. Now, we never break out of the loop. We don't ever break out of the whole entire thing. Rather, we just skip that singular pass in this for loop. So what should we expect here? we should expect to see something like 0, 1, 2, 3, 4, right? And then we skip to 6, 7, 8, 9. And we can see that's exactly what we get. And now if we were to move our print statement up here though, this continue block would not even matter, because we've already printed our 5 in that specific iteration. So now if we print it and then we evaluate the conditional equal to 5 and continue, there's nothing else after this block that actually matters. So we should just get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can see that's true right here. So the order matters in Python. In the next file, I'd like for us to cover your first while loop. A while loop, as I mentioned, repeats as long as its condition stays true. The important difference from a for loop is that while loops don't automatically move on to the next value. You have to update the variables involved in the condition so the loop can eventually stop. Here we can use a counter, kind of like exactly what a for loop does behind the scenes. So we call this 0, and then we can do something like while count is less than 5. While counter is less than 5. We can print count, counter, and we can increment counter by 1. This would give us 0 through 4. The most important line here is this counter equals counter plus 1. That's what changes this condition up here over time. Each loop, counter increases, and eventually counter is no longer less than 5, so the loop ends. A beginner mistake would be to forgetting to update count. If you don't ever increment counter, then counter stays 0 forever and the while loop will run forever, creating what we call an infinite loop. Since we have a guard in place, that doesn't matter. 0, 1, 2, 3, and 4. Now, let's say we commented this line out. Now we would just see a whole sea of zeros. And that's what we call an infinite loop. In the next file, I'd like for us to cover looping over a list. A quick note, we're using a list here to show what looping looks like in real code, but we'll cover lists in the next episode, and we'll formally go over lists. For now, treat a list as multiple values stored together in order. Say we had a names list right here. We can have John, Ava, Steve, and say my name. We can do something like for name in the list of names that we just defined. And we can print each name. Now, names here has basically replaced our range from earlier. So for every iteration of the for loop, instead of name being 0, 1, 2, 3, and 4, our name variable will update from John to Ava to Steve to Kelvin. And we can see that this will print exactly that. This is also a very common use for loops. Do something once for each item in a collection. In this case, the collection of items is a list of names. Let's go over some more simple loop patterns. Say we wanted to approach counting, summing, and finding in a collection of values. The structure is fundamentally the same every time. First, we initialize before the loop, update inside the loop, and then use the result after the loop. For counting, we could do something like this. Numbers is equal to a list of 2, 7, 4, 9, 10, and 3. And for our for loop, we'll look something like, and we'll have a count variable initialized to 0, and then we can do something like for n in numbers. Could even do something like for number in numbers, but we'll stick with n. If n is greater than 5, we can increment count by 1. And then we can print count. What this is doing here is counting how many numbers are greater than 5. Count only changes when the condition is true. If the condition is false, count stays the same. In this scenario right here, we'll have 1, 2, and 3. So we should get a count of 3. See, that's exactly what we get. What if we wanted to sum the values in the list? Again, very simple. 2, 7, 4, 9, and say we wanted to find the sum of those numbers. And then we can have total is equal to 0, and for n in numbers, total is equal to total plus n. Since we start at 0, it's going to do 0 plus 2, and then 2 plus 7, and then 9 plus 4, and then 13 plus 9, which gives us 22. See, that's exactly what we get. Now, what if we wanted to find the first match in a collection of values? Say we had a numbers list that had 2, 7, 4, 9, 10, and 3. And say we wanted to find the first occurrence where n is greater than 8. Now say if n is greater than 8, we want to return the number that our loop has found to be greater than 8. We can set that at n, and then we can break out of this loop since we only need 1. In this example, right, we would go through 2, 7, 4, and 9. 9 is the first occurrence of a number greater than 8. So we simply set found is equal to 9, and then we break out of the loop, and then we print found. We ignore everything else afterwards, even though 10 is still greater than 8. And we see that that's exactly what we get. That's it for the lectures in lesson 4. As always, we're going to check our Git status. I've added a intro.py. We can ignore that. We can also ignore this. We'll add git add lesson 4, since that's all we want to contribute to the course repository. Write a git commit message, lecture 4 loops. Oops. And then we can push. And this will be saved in our course repository. That's loops at a beginner level. You now understand what the range function does, how for loops repeat code, how loop variables work, how to combine loops with the conditional logic that we covered last episode, how break and continue affect loop flow, how while loops repeat based on a condition you control, and the 3 most common loop patterns, counting, summing, and finding. In the next episode, we'll formally cover the lists. You've seen them briefly here, but next time, we'll slow down and explain what lists are, how indexing works, and how to work with them confidently. Thanks for watching, and I'll see you guys in the next episode. Hey everybody, my name is Calvin, and welcome back to episode 5 of my Learn Python series. Today, we'll be covering lists and their relevant methods in this video. A list is one of the most important core data structures in Python because it lets you store multiple values inside one variable. Instead of managing a bunch of separate variables like student1, student2, student3, you can store them together in a list and work with them as one collection. Lists show up everywhere in real Python. Names, prices, rows of data, tasks, file paths, API results. Anything where you have many values instead of one value. The big idea here is that the list is ordered, meaning items stay in a specific order, and each item has a position you can access within the list. Once you understand that lists are ordered and index-based, most list operations start making sense. You can access by index, you update by index, you add or remove items, and the list shifts to keep that order. As always, the course repository will be linked down in the description. I also recommend watching the earlier episodes before this for the best learning experience. A link to episode 4 is in the right corner. Be sure to check it out if you haven't already. Without further ado, let's jump into lesson 5 of our Learn Python series. We'll create a folder for our exercises. Like we did before, lesson 5, and we'll initialize 5-1.py. In our first exercise, I want to talk about what a list is and how to read it. A list is written with square brackets. Inside the brackets, you put values separated by commas. The simplest way to think about it is this. A list is a container that holds multiple values in order. We're going to create 2 lists, one list of names and one list of scores. Say we had a list name of John, a string value, Jane, a string value as well, and Kelvin, which is another string value. And now let's have a score list called, or scores rather, that contains corresponding scores. Let's give John a 98, Jane a 100, and Kelvin 100 as well. And then we can print it. And we'll run this. When you print a list, Python shows you the entire contents at once using brackets. These will look very similar to how we defined them up here. This is helpful early on because it makes it obvious what's inside and what order things are in. Now, each item in a list has an index. The index is the position of an item. In Python, indexes will always start at 0. So the first item in a list is at index 0. That's how Python works, and it's one of the most common beginner mistakes to forget. What do I mean? So for this list, we have John, Jane, and Kelvin. Our index mapping is that John is at index 0 of the names list, Jane is at index 1, and I'm at index 2. Same thing for the scores. In the scores list, we have 98 in index 0, a 100 in index 1, and a 100 in index 2. We can access the items by index. The syntax is very simple. Say we wanted to access Jane in names. We can do something like this. Print names, left bracket, 0. The index is defined within these brackets right here. It has to be these square brackets. We can do the same thing to get all the objects in the list. Say we wanted names 1, and then let's also retrieve names 2. We'll comment this out so we can just see what this prints. And we can see that we get John, Jane, and my name. Now, as a reminder, if the list contains 3 items, then the last index will be a 2 and not a 3. Be sure to remember that. Now, we can also get the length of the list. It's pretty easy as well. All we need to do, it's very simple. We'll just use the length function. We're going to put print length, or len, and then we put in the names list. Now, we get 3. That 3 corresponds to the amount of items within this specific list. Now, if we expanded it, say to add Joe, now we should expect to see a length of 4. And you can see that that's exactly what we get down here. Now, a trick that we can do here is if we wanted to get the last item in a list, it's as simple as using the index of the length of the list minus 1. What do I mean? What if we wanted to get Joe? We can do something like print names length names minus 1. And that will give us Joe. Now I want to touch on negative indexing. Negative indexes count from the end of the list. Now indexing here is a little bit different. If we wanted to get the last item in the list, for the index that we use, it'll be a -1. -1 means the last item, and -2 means the second to last item, and so on and so forth. Let's see it in action. So say we wanted to get my name using negative indexing. We can do something like this and pass in a -2, since the way that we can get Joe is with -1. So the second from the last is a -2. And we can run this and you'll get my name. And we can do this for every single name in the list. And you can see that we are able to get all 4 names in the list using negative indexing. So now you have 2 ways to reach the last item. We can use names -1 or names length of names -1. The -1 version is shorter and more common and avoids having to calculate the last index manually. Let's move on to the next exercise. Create a 5-2.py. In this file, I want to touch on types inside lists and nested lists. A list can hold any type. It can hold strings, integers, floats, booleans, and even none types. Python does not force all list items to be the same type. We can do something like this. Say we had a mixed list and we had Madison in the index 0 of the mixed list, 21, which is an integer, in the index 1 of this list, and say we wanted to have a boolean in the last position in the list. This is completely valid Python. The reason Python allows this is because, as we touched on before, Python is dynamically typed, and lists can store references to any kind of object. Now, one thing to note, even though mixed lists are allowed, most beginner programs and most real programs keep lists consistent because it's easier to reason about and easier to process. For example, a list of names is all strings, a list of prices is all floats, a list of IDs is all ints. While everything is the same type, it's easier to do the right operations on every single element. Let's print our mixed list, and we'll see that there is no error thrown, and this is a completely valid Python statement. Now, we can also nest lists, which means lists within lists. You'll see this later when you have to deal with things like rows and columns, tables, grids, etc., etc. Say we had a nested list called matrix is equal to a list with another list that stores 1, 2, and 3, separated by a comma, and then 4, 5, 6 for the second list inside the nested list. Now, let's do a couple of indexing problems. Now, we can print the whole entire matrix. We can do this by simply passing in matrix to the print statement, and we get our nested list, like so. We can also get individual objects within the nested list. If we did something like print matrix with an index of 0, this will retrieve the 0 index list within the nested list. So we'll see a 1, 2, 3 list being printed with this statement. 1, 2, 3, as you can see down here. Now, do the same thing with the other list. Matrix, and we can use negative indexing, -1. This should get us 4, 5, and 6. Now, we can go even further than that. Within the list that we retrieve, we can also index within this specific list. So say, for example, we wanted to get 2 in the first list. We can do something like print matrix at index 0 at index 1. And this will print us the 2 integer within the first list. And we can do the same thing if we wanted to get the integer 6 in our nested list. We can take our prior print statement from before, and all we need to do is take this statement right here, since this gives us the second list, and provide the index of the number that we want. So since we want 6, we can do -1, -1. And we'll see that we'll get 6. The key idea here is every pair of brackets indexes one level. The first bracket picks the row. Second bracket picks the element inside that row. You could go on and on and on, although I don't recommend it since it can get pretty messy. Let's move on to our next concept. In our third exercise, I want to go over mutability. Lists are mutable. That means once you create a list, you can change its contents. This matters because it means the list can pretty much evolve over time. You can update values, add new ones, remove old ones, and keep the same list variable. To update a list item, it's as simple as just assigning it to an index. Say we had the names list from before. Let's get it from here. And let's say that we wanted only a list of J names. So we'd have to replace my name with something that starts with a J. All we need to do here is take names at index 2 is now equal to Jordan. Now we can print this. Let's print the names before as comparison. And as you can see, we've successfully replaced my name with Jordan. It doesn't create a new list. Rather, it takes the old list and replaces the value inside the list. It directly overwrites that spot. Now, we also want to note that you can only assign to indexes that already exist. If your list has 4 items, the valid indexes are 0, 1, 2, and 3. If you try to assign something at index 4, Python will raise an index error because there's no slot there. Say we wanted to add my name back in to the names list. Say we wanted to append it to the end of the list right here. Now, we would think that all we need to do is do something like names 4 is equal to my name, but we can't do that. If you try to assign to index 4 here, Python raises an index error because there is no slot there. If you need to add a new item, you don't assign it to a brand new index. We can use list methods like append or insert, which actually expand the length of the list. We also want to keep in mind that updating an item does not change the length of the list at all. It keeps the same number of items because you're replacing and not adding. In our next exercise, let's go over how we would properly add it. Say we took our list of names from before, and say we did want to add my name back in. At this point, this is what the list looks like, and say we wanted to add Kelvin at the end of this list. we can do something like names.append, which is a method that you can use for lists to add an object to the end of a list. So all we're doing here is appending my name. Let's print the length of names for demonstration right here, and then also after we append, and we'll also want to print names. Now we can see if our list from before has a length of 4. Now we have a list length of 5, and now our updated list looks something like this, with my name attached to the end. One thing to note about the append method is that it will always add to the end. Now, what if we wanted to add a value at a specific position? Say we wanted to add my name back at index 2. In this case, we would use the insert method. In the insert method, we do it like this. We'll have the index that we wanted at, which in this case is 2, comma, the value. So now in this case, we'll see my name back at index 2. Now, Jordan and Joe have both incremented their index by 1, since we added my name in the middle of this list. Now, what if we had 2 list of names? Names 2, with a few other names that we wanted to add to it. Say we had Poe, Jacob, and Jonathan. Oops. Say now we had 2 lists of names, our original list of names and a new list of names that we want to add to the end of our original names. This would be also pretty easy. All we need to do is use the extend method. So we can call the extend method by doing names dot extend parentheses, and then we pass in our second list of names. Now, if we wanted to see our updated names list, we can do the print function, and we can see that the second list is just extended on the end of the first list. Note that the names too will not change here, because all we're doing is updating our first names list. Let's move on to the next exercise. In this exercise, we've dealt with adding things to lists. What if we wanted to remove it? Let's use a new list of numbers. Say we had numbers equal to a list of 1, 2, 3, and 4. What if we wanted to remove 3 from this list? If you know the value that you want to remove, we can just simply use the remove method. And we can call it like this. And we can pass in the value that we want to remove, which in this case is 3. Now let's run this. And as you can see, our remove method removed the 3 in the list. Note that the remove method only removes the first occurrence of that value. Say we had another 3 at a later index. This would still only remove the first 3. If the value isn't in the list, say we wanted to remove a 0, it would give us an error because the value is not in the list. If you know the index of the value you would like to remove, you can also use the pop method. Our pop method here will take an index and remove that value at that specific index. So say we wanted to remove, let's say, 4 right here. We can pass in an index of -2. And now we can see that our 4 has been removed. You can also use the pop method without anything inside. In doing so, the default here is that it will just pops the last item in the list. So in this case, we would pop the 3 off this list. What if, say, we wanted to remove everything in the list? In this case, we can also use the clear method. Make sure that you call clear using a dot clear parentheses. And now we can see we cleared every single thing out of our numbers list. Let's move on to our next exercise. In this exercise, I want to cover slicing. Slicing is how you take part of a list. The syntax here is list, bracket, start, colon, stop. The start is included and stop is not included. That means it takes items starting at start and ending right before the stop. Say we have a simple list of numbers. Is equal to 1, 2, 3, 4, and 5. And 6. Say we wanted to get a sublist that contains the items from 0 to index 2. In this case, we can use slicing to get that list. So numbers, bracket, 0, 3, which should give us 1, 2, and 3. Index 0, index 1, and index 2. Notice how 4 isn't in here because it stops before the stop. What if we wanted to get the indexes from, say, 2 to the end? We'll do something like this. And we can get 3, 4, and 5, not including 6. One thing to note here is that slicing does not modify the original list. So if we printed numbers right here, and we printed numbers right after our slice, the number list stays the same because we didn't modify the list like we did previously. Slicing is also pretty flexible. You can give it a really big index. Instead of crashing, it gives you everything in the list if the index that you want at the stop exceeds the length of the list. Let's move on to our next exercise, 5-7.py. In this exercise, I want to cover copying lists. One of the most important list lessons is that assignment does not copy a list. It makes two variables point to the same list. So if you do something like b is equal to a, b is not a new list. It's a second name for the first list. So say we had something like a is equal to 1, 2, and 3. And we set b to a. What if we called the method of append on the list b and print out both a and b? Since we only call it on b, you would expect that our a list stays the same, but instead our b list has 1, 2, 3, and 4. But we can run this and we see that it's not the case. Both variables, instead of creating a copy of the list, will now reference the same exact list, which is the 1, 2, 3, the original list that we created. Now, what if we didn't want this? And what if we wanted an actual copy? Instead, we can use the copy method for assignment, a.copy. Now, if we did the same exact thing, we can get 1, 2, and 3, and then now 1, 2, 3, and 4, because now b is now a copy of a. If you accidentally alias lists like this, it's possible that you'll get bugs where something changes rather mysteriously, but rather it's just two names pointing to the same object. In our next exercise, we'll cover another few key methods. Say we had our names list from before. What if we had an extra Joe in here? What if we wanted to know how many times Joe appears within the list of names? We can use the count method. We can type in names.count and then pass in the value that you want to count. Whoops, we need to print this. And now we can get 2 because Joe appears twice. Say we wanted to find the index of the first Joe that shows up in this list. Now we can use the index method. Names.index. Oops. Our index that our first Joe appears at is at 0, 1, 2, and 3, index 3. If the value isn't found, it'll raise an error. Now what if we had a numbers list? What if we had a random list of numbers? We can see that this is not sorted at all. It doesn't go in ascending. We can see that this is not sorted at all. As in, it doesn't go in ascending order. We can call numbers dot sort, and this will sort the list of numbers. Whoops. We can see that now our list of numbers is sorted. What if we wanted this in descending order, as in 9, 5, 4, 3, 2, and 1? We can do numbers dot reverse to reverse the list. Now we can print numbers again. 9, 5, 4, 3, 2, and 1. Our reverse method reverses the list in place. And those are the exercises that I wanted to cover in this video. As always, we're going to do get status and see what changed. In this case, we added a lesson 5. You can ignore all of these. We'll do our get add, lesson 5, get commit, lecture 5 lists, and then push to the course repository. And that was what I wanted to cover in our lists episode. Lists are one of those things you're going to use constantly in Python. So the goal here isn't to memorize every single method. It was to get comfortable with the idea of working with a collection of values and being able to confidently access and change what's inside. Thanks for watching, and I'll see you guys in the next video. Hey everybody, my name is Kelvin, and welcome back to episode 6 of my Learn Python series. Today, we're going to be working with strings in Python. Strings are just text, and you'll use them constantly, even in simple programs, because names, messages, labels, file names, and a lot of real data show up as text. The goal of this video is to get comfortable with basic string operations that you'll be using all the time as a Pythoner. Creating strings, recognizing what kind of value a string is, combining strings, using a small set of core string methods, and doing simple checks on text. As always, the course repository will be linked in the description. If you haven't seen the earlier episodes in this series, be sure to check them out for the best learning experience. Without further ado, let's jump into the exercises. Like usual, we'll be creating a lesson 6 folder to store everything that we're going to cover here today. And we'll create a 6-1.py. In the first exercise, I want to get comfortable with what a string actually is. In Python, a string is a value that represents text, as I said. The simplest way to recognize a string is that it's wrapped in quotes. If it's in quotes, then Python will treat it as text. If it's not in quotes, it might be some number, a boolean, or even something else. This matters because Python treats different types differently. You could do math with numbers. You can combine text with other text. But Python won't automatically guess what you mean if you mix them. So early on, it's useful to confirm what type you're dealing with or using the type function. Say we had a name variable set to Joe. City variable is set to a string with Boston. And say we had a course variable that we initialized to Python 101. Now we can print this. Name, city, course. We can print out the three variables. We can see that we get the three strings. Now let's check what type they are. We can wrap the variables in the type function, like so. We can see that Python recognizes all three of these variables as the type string. It doesn't matter if you use double quotes or single quotes. They will be the same. So if we used single quotes for Joe, double quotes for Boston, double quotes for Python 101, Python will still recognize it as string because they're functionally the same. What confuses some beginners is that a string that looks like a number is still just text. It's not a number until you convert it later. This matters a lot later when we start taking user input, because input usually comes in as a string even if the user typed digits. Say we had an age string that stored 21, but we also had an age integer value that was 21. And then we printed out each one and their corresponding type. And we can print this. Oops. And we can see even though the print statement will give us the same thing for the variable value, we have different types. The age text giving us a string variable, and age number gives us an int. It's the same looking value, but it's a different type. Let's jump into the next exercise. Here, I want to cover length, indexing, and slicing. We're going to keep this short because we already covered this. in the last episode with the lists. Strings are sequences too, so they have a length. You can index them and you can slice them. The goal here is to remind you that these sequence tools work the same way on strings. Say we had a word variable and we initialized it to Python, a string Python. We can get the length of this string using the length function. We can get the uppercase P using our 0 index. We can get the last N using a -1 index. And we can slice this like a list. Let's run this. And you can see that's exactly what we get. Our word variable here has a length of 6 because there are 6 characters. Word 0 here will give us this P right here. -1 will give us this N right here. And then this slicing will give us PYT because we're starting at index 0 and we're ending at index 2. In this case, it would be this string right here, PYT. If these methods are unfamiliar to you, be sure to check out episode 5, where we cover this in much more detail. Let's move on to the next exercise. In this exercise, I want to cover combining strings. One of the most common beginner tasks is building a message out of smaller pieces of text. The simplest way to do that is simply with concatenation with the plus operator. The important rule is that plus only works cleanly when both sides are strings. For now, we're keeping it simple and only combining string pieces with string pieces. Say we had a first name variable that had my name in it, and then a last name variable with my last name. We can simply do something like this if we wanted a string with Kelvin space Lynn. We can have a full name variable is equal to our first variable plus a space plus my last. Oops. This should not be Lynn. Got caught up in that. Okay. And then we print the full name. And we can see that we have a new variable now, a full name that is Kelvin space Lynn. We're taking the first name string, adding a space string in the middle, and then adding the last name string. So the result is a brand new string that contains everything combined. What if I didn't have this space here? This is something that I always mess up on, but if you add them, it'll be Kelvin Lynn since it doesn't automatically add a space. Notice the text inside these double quotes is simply a space. I could do the same thing with a dash, and we get Kelvin dash Lynn, but we'll keep it as space for now. Now, what if I wanted to expand full name even further? That'd be pretty easy as well. We just do full name is equal to a string plus full name right here, and then we can print full name again. Oops. And now we can see that our full name in its end state is Professor space Kelvin space Lynn. That's how to concatenate strings. Pretty simple, right? Let's move on to the next exercise. Here, I want to point out the fact that strings are immutable, so methods return new strings. This is unlike lists, if you paid attention in the last video. This means that you can't change them in place. You can't edit the string directly like you could in a list. Instead, whenever you do something like lowercase a string or strip spaces, Python creates a new string and gives it back to you. This matters because beginners often expect a method call to change the original variable automatically. With strings, most methods return a new string. If you want to keep the new version, you must store it in a variable. Say we had a variable with hello. Now we're interested in seeing the original state. Then we'll lowercase the text. No need to worry about this just now. We'll cover this just in a second. Print. Just know that this lower here is a method call. What should we expect here? The original prints as capital H-E-L-L-O. The lowered version prints as hello, all lowercase, and the original prints as capital H-E-L-L-O again. We changed nothing about the text. We created a new string, and then we stored it in a lowered variable. We can run this, and we can see exactly what to expect here. Change these two L's to capital to show it. And you can see, and that's exactly what we expect. Now let's jump into some useful string methods that you'll use in your day-to-day work. The first method we'll cover, we just used, is the lower method. Lower returns a new string where every letter is lowercase. This is useful when you want text comparisons to be consistent because all uppercase hello and all lowercase hello should often be treated the same. Say we had a text with hello, hello, world. Notice the different capitalizations. We can print the original. We'll also use the lower method on it. I'll call the lower method right here. Now we should see the lower line right here print hello world all lowercase. Run this, and that's what we get. Notice the original prints are unchanged before and after, like before. Now we have an upper method. It pretty much does the opposite thing to the text. Now, all lowercase values in this text will be capitalized. I can run this. Our new text right here will print out hello world, all capitalized. This is useful for normalization or for making output stand out. Now I want to cover strip. Strip returns a new string with white space removed from the beginning and end. White space means tabs, spaces, and new lines. Strip does not remove spaces in the middle of the string. It only cleans the edges. So we can take the string and we can modify a bit, add some space, add some white lines, or I have a couple spaces on each edge. And we can use the strip method to get rid of the white spaces. This will give us hello world like before, including the space inside. It will only get rid of these values right here. Run it. And we can see that's what we get. We can see that the original printed with a lot of spaces, but this one right here has no spaces. Now we can cover a fourth method, replace. Replace returns a new string where occurrences of old are replaced with new. This is useful for swapping words or cleaning up text. In Python, replace replaces all occurrences until you tell it otherwise. Say we modified our string again to have hello. We'll keep it simple and keep it lowercase for now for the demonstration. What if we wanted to replace both hellos with goodbyes? That'd be pretty easy. We can do the same thing. We can use the replace method. We call it the same way. The first parameter you put in is the word that is going to be replaced, in this case, hello, and then the value you want to replace it with, which in this case is goodbye. As you can see, now the hellos are replaced with goodbyes. Again, note that the original remains unchanged. Now, what if we wanted to do multiple operations on the text? Say we wanted to remove the white spaces from our printed string. That'd be pretty easy. We can just call the strip method in here. This method call right here will remove the white text, and then our replace will take this output and then replace hellos with goodbyes. And we can see that now the white space is gone. And we can keep doing that with all the methods that we just covered. What if we wanted everything to be uppercase? We can just simply call upper. Moving on to the next exercise, I want to cover some simple basic conditional checks. Again, remember that checks return booleans, either being true or false. Our first check will be the in keyword. The pattern substring in string checks whether the substring exists anywhere inside the string. It returns true if it's found and false if it's not. Say we had another text that contained hello world. And we wanted a way to see if hello was in our text. We can do something like this. Hello, the string hello in text, and this is a conditional statement on its own. We should expect to see true here because hello is indeed in our text hello world. Now, what if we wanted to find bye in our text? That wouldn't work because bye is not in our text. This should print false. Another method that we'll cover is starts with, which takes in a prefix. The starts with method checks whether a string begins with a specific prefix. It returns true if it starts with that prefix and otherwise false. Say we had our hello right here, and let's say we wanted to check for the HEL prefix. We can write a conditional statement looking like this. Text dot starts with and we can pass in HEL, and this should give us true because it does start with HEL. Now, what if it doesn't start with a prefix? Say we wanted to check for bye instead. Bye is nowhere in hello world, and it's certainly not a prefix, so again, we should see true and false. You can see that that's what we get. Ends with is basically starts with backwards. We check for a specific suffix. So in this case, what if we wanted to check whether or not our text had a suffix RLD? We can pass the RLD in, and it'll check the string. This should return true. Now it doesn't end with bye, so this should return false. And we can see that it works. Now, I also want to make sure that you guys understand that cases do matter. Say our text had world with the last 3 letters capitalized. Now, this will give us false, because even though the letters are the same, RLD, one's capital and one's not. And we can see that our new call is false. This would be a pretty easy fix, since all we would need to do is lowercase the whole entire text first and then check. And we can do that using our lower method like before, and this should give us true. As always, we'll do our git workflow. We'll do git status, see what changed. In this case, we have a lesson 6 folder. We can see that this is unstaged, so let's stage our lesson 6. Let's commit it. I'll call it, and we'll have a commit message lecture 6, which dealing with strings, and we'll push it to the repository. And that does it for the string episode. The goal here was to make strings feel normal and usable. You learned how to create strings and confirm their strings, how string sequence behavior like length and slicing still applies from the list episode, how to combine strings to build output, how core string methods work and what they return, and how to do simple checks that give you true or false. Thank you for watching, and I'll see you guys in the next video. Hey everybody, my name is Calvin and welcome back to episode 7 of my Learn Python series. Today, we'll be covering the math you need as a beginner Python programmer. I'm talking about the everyday operations you use in real programs, adding, subtracting, multiplying, dividing, keeping track of totals, and understanding what Python is doing when it produces a result. This is important because most programs do something with numbers. Whether you're working with money, time, scores, counts, measurements, or anything else, you need to be comfortable with basic numeric operations and the numeric types that Python uses. You also need to understand what kind of number you have, because an integer data type behaves differently from a decimal number, and division behaves differently depending on what operation you use. Before we jump into the code, there's something I'd love to share with you guys. Have you ever wondered how the biggest companies in the world organize, sort, and analyze their data? It's from the work of data engineers. Data engineering is the backbone of modern analytics, business intelligence, and machine learning. Data engineers in the US earn around an average of $130,000 per year, with some even making over $200,000 annually. Hi, my name is Calvin Lin, and I wrote this book because this is something that I wish I had when I first started out. From databases, data warehouses, and real-time data streams, this book will give you a great foundation to launchpad your data engineering career. This is Modern Data, from Ingestion to Production. Available on Amazon, Apple Books, and Barnes & Nobles, so get your copy today. My book, Modern Data, from Ingestion to Production, is available on Apple Books, Amazon, and Barnes & Nobles, so please check it out. Hopefully you guys can learn something from it, and I'd love to hear any kind of feedback you guys might have. Let's jump into the code. We'll create our Lesson 7 folder, like before, and we'll create our first exercise file. Before we do any math, we need to understand the two main numeric types that we'll be using constantly, the int and the float. We've gone over these before, but we'll dive into it deeper here. An int is an integer. It represents whole numbers like 0, 5, -10, 42. A float is a floating point number. It represents numbers with decimals like 3.14, 19.99, or -0.5. Again, we don't manually declare types in Python. Python will decide the type based on the values you assign. Again, that's called dynamic typing, and it's convenient, but it also means you need to know what type you're working with when you do math, because the output type can change depending on the operation. Say we initialized an integer, a, and we set it to 10. Now we had a float, and we set it to 3.0. The way we initialize an integer is just a whole number like this, and a float will be a decimal with a period. We can confirm this in Python by running our simple print statements, and we can check the type of A, and let's check the type of B. We can run this, and we'll see that A is 10, a class of integer, and B is 3.0 with a class of float. We also need to understand that even if two values look similar, they can still be different types. What if we wanted to initialize our integer to 3? These are pretty much the same value, but the data type is different because A remains an integer. We didn't put a .o right after the 3, whereas in B we did. And we can confirm this in Python as well. 3, class of integer, and 3.0 with a class of float. Now, what if we mixed an integer and a float in some mathematical operation? Python will usually default to giving you a float result because it needs the decimal precision to represent the answer accurately. For example, what if we had a variable result is equal to 10 plus a 10 integer plus a float 2.5. This will default to a float data type, even though the 10 right here is an integer. We can test this using our print statement from above. And we can confirm this. And that's what we expect. The main takeaway here is that integers are whole numbers, floats are decimals, and mixing them will usually produce a float. Let's move on to the next concept. The next concept I want to cover are the basic arithmetic operators, like addition, subtraction, multiplication, or division. They're very easy to understand because they read normally. We'll initialize a to a integer 10 and b integer 3. We can perform addition by simply using the plus sign. So a plus b will add a and b. Run this, and we get 13. Integer 13. That's simple addition. Subtraction is basically the same, but this time we'll use the subtract sign. We'll run this, and we get 7. Basic multiplication is the star symbol right here. This one you'll need to remember, it's not an X, it's the star symbol. You can run this, we get 30. And division will be the slash. The slash operator always performs true division and returns a float even if the division is even. What do I mean by that? Say we had 10 divided by 2. You would think this would give us an integer 5, but that's not how it works. This, a single 1 right here, will give us a float irregardless of whether or not these are integers. And we can confirm this by checking the type. I'm going to see 5.0 with a class of float. This is normal. We'll cover another type of division later that will help us negate this. In the next part, we'll talk about some other different types of division. In the file 7-3, we'll go over those division operations. The first is floor division, which is defined as just slash slash, 2 slashes in a row. Whereas regular division was a single slash, our floor division is 2 slashes. Again, we have 10 and 3. Now we can print a slash slash b. And what this will give us is 3, because 10 divided by 3 is 3.33. And then what the floor division here, instead of giving us a float number, 3.333, it'll drop the decimal part and simply give us the whole number. So we can run this, and we'll see that we get 3. And we can also confirm that this is a type integer. As well, class integer. Another operation I want to cover is modulo. The modulo operation gives you the remainder after division. The modulo operation in Python is represented by the percent sign. Now, what if we wanted to find the remainder of 10 divided by 3? We should expect 1, because 10 divided by 3 is 3, with a remainder of 1. Now we can check the same thing right here. This will give us an integer as well. C1 with a class of integer. We can also adjust the numbers in the case where it divides evenly. So for example, here, instead, we'll change b to 5, and we should expect for this to give us 0. We can see that this correctly gives us 2, and a modulo b gives us 0, because there is no remainder. Most times, people will use modulo to check odd versus even. This is done by using a number modulo 2. Based on simple mathematics, if the number is odd, it produces a remainder of 1, whereas if it's even, it'll produce 0. So this can be used in conditional checks to check whether or not a number is odd or even. Now we can confirm this right here. 1, and 0, what we expected. The next concept I'd like to cover is the order of operations and parentheses. Python follows standard math order of operations. Think PEMDAS. Multiplication and division happen before addition and subtraction. Parentheses override everything and force Python to evaluate the parenth part first. We can confirm this in Python with two expressions that look similar but produce different results. For example, we have a 2 plus 3 times 4. And now in the order of operations here, this should do 3 times 4, and then that gives us 12, and then we add 2, which gives us 14. Now, what if we added a parenth around the 2 plus 3? Now, this will give us a completely different answer. Now, because of the parentheses, we do the 2 plus 3 first, and then now it's 5 times 4, and we should expect 20 here. We can run this, and that's exactly what we get. It's also good to remember that parentheses are useful for readability, even when they're not strictly needed. When you're a beginner, clear code is more important than clever code. You need to make sure people are able to read your code, and you yourself are able to read your code. For example, if we had a subtotal and a tax rate, we can set total is equal to the subtotal plus parentheses subtotal times the tax rate. Technically, we don't need the parentheses there because of the order of operations, but it's definitely a lot more readable that way. The parentheses makes it obvious that the tax is calculated first and then added. The next concept I want to cover is working with negatives and absolute values. Negative numbers are very common. Think temperature changes, money spent, account balance changes, and differences between values. Say we had a variable called change is equal to negative 15, and we can denote negative values by the minus sign in front of the number. And we can print this, and we'll get the output that's very similar to a positive integer. In this scenario, we would just get negative 15. Now, what would be the absolute value of change? If you remember in math class, the absolute value of the change variable of negative 15 is simply 15. And we can find that in Python by using the abs function. So let's set that to a variable called distance, have the abs function right here, and we pass in change. And then we can, did not mean to put negative 15 there. Put in change, should be the change variable. And we can print distance. And the first thing that should be printed is negative 15, and the second should be 15. We can see negative 15 and 15. We can do something a little bit more complicated. Let's say we had a variable a, and we set that to 10. B is equal to 18. Both are positive integers. Now, what if we wanted to find the difference between a and b? We can do this using the subtract operation, a minus b, and then we'll print diff. 10 minus 18 will give us negative 8, and in this scenario, that makes diff negative 8. And we can print this, and we'll get negative 8. And we can also find the absolute value of diff as well, which in this case is 8. In our next exercise, I want to cover rounding and decimals. Since we want to work with money or measurements, you don't really want to print a value with a long decimal tail. The round function rounds a number to a certain number of decimal places. Say, for example, we had a float called price, and we set that to 19.9876. We know that we would just round this at a store or something to $19.99. But if we printed it, we would get 19.9876 because it doesn't round for us. We can find the rounded number by using the round function. We pass in price, and then we also pass in how many decimal places we want. In this scenario, we want 2 decimal places because it's $19.99. You can't really have half a cent. We can make this human readable by rounding the price variable to 2 decimal places. And we print this and run it. See that it's rounded now. I also want to point out a quirk with floating point numbers. Floating point numbers can sometimes produce results that look slightly off. This is not because you're doing the math wrong, but rather it's how computers store decimals internally. For example, if we had print 0.1 plus 0.2, we get 0.3 with a bunch of zeros and 4. We know that this should just give us 0.3, but the quirk makes it so that there's the 4 at the end. Again, that's just how computers store decimals internally. The last concept I want to cover for this video is typecasting. Sometimes you need a whole number and sometimes you need decimals, and Python will not automatically do what you want. As we covered before, the int function converts to an integer, which means it drops the decimal part, and it does not round, and it cuts off the decimal. The float function converts to a float, giving you a decimal representation of the int that you just converted. Say we had a float called x, and we set that to $3.99. And say we wanted to typecast that to an int. In this case, you might think that we would get 4 because this is closer to 4 than it is 3, but that's not the case. The int typecast here will simply remove the .99, and then in that scenario, that gives us 3. It doesn't round for us. I'm going to execute that, and you can see that's what we get. Say we had another variable and we set it to 10. What if I wanted to make that a float? It's as simple as typecasting it to a float. And we should get something like 10.0. And as we said it would, 10.0 is printed. And that does it for episode 7. As always, we're going to be checking our Git status. We can see that we have a lesson 7 folder. We'll git add lesson 7, git commit, add episode 7. I'll push this to the repository. The goal of this video was to make you comfortable with the math that you'll use constantly in beginner Python programs. You'll learn the core numeric types, how Python decides int versus float, the basic arithmetic operators, how division behaves, how floor division and modulo work, how order of operation works, and how to use parentheses for clarity, how to round values, and how to convert between int and float when you need to. In the next episode, we'll move on to functions. Functions are going to be how we tie all the episodes that we've worked up to until this point together. So stay tuned. And as a reminder, be sure to check out my book, Modern Data, From Ingestion to Production. And thanks for watching. Hey everybody, my name is Calvin, and welcome back to episode 8 of my Learn Python series. Today, we'll be covering functions. Functions are the moment where your code starts to look like real software instead, of just a bunch of lines in a file. Up to now, every script we wrote in the previous lessons ran basically top to bottom. That's fine for tiny examples, but what happens if you want to repeat logic or you want your code to be readable a week later? In that case, you need structure. Functions will give you that structure. What is a function? A function is a named block of code you can run whenever you want. You can feed it inputs or parameters, and you can have it hand you back an output. That's pretty much it. But the simple idea here pretty much unlocks everything in software engineering. you can reuse without copy and pasting, you have cleaner logic, easier debugging, and code that's naturally testable. In this video, we'll be using all the concepts that we covered in lessons 1 through 7 and wrap them into a nice bundle, that being the function. As always, the course repository is linked in the description, and I also recommend watching the earlier episodes before this for the best learning experience. Before we jump into the code, I have something I'd love to announce. Have you ever wondered how the biggest companies in the world organize, sort, and analyze their data? It's from the work of data engineers. Data engineering is the backbone of modern analytics, business intelligence, and machine learning. Data engineers in the US earn around an average of $130,000 per year, with some even making over $200,000 annually. Hi, my name is Calvin Lin, and I wrote this book because this is something that I wish I had when I first started out. From databases, data warehouses, and real-time data streams, this book will give you a great foundation to launchpad your data engineering career. This is Modern Data, from Ingestion to Production. Available on Amazon, Apple Books, and Barnes & Nobles, so get your copy today. Be sure to check out my book, Modern Data, from Ingestion to Production, available on Amazon, Apple Books, and Barnes & Nobles. Let's create a Lesson 8 folder like we've done with the previous lessons. Initialize our first file. We'll call it 8-1.py, like we have before. In this first section, we're going to build basically the core mental model for functions in one place, so we don't have to keep jumping around. The goal is to understand what it means to define a function, what it means to call it, what parameters are, and what it means to return a value. If you get this part, everything else in this video is just variations upon this pattern. The first thing to understand about a function is that defining a function does not run it. Defining a function is basically like writing down instructions for your computer and then giving it a name. The code inside only runs when you call the function. Then, in this function, we'll add parameters. Parameters are just variables that get created when the function is called, and they are filled with the arguments that you pass in. Finally, we'll add return values. Returning is how a function hands a value back to the rest of your program. While we have used printing before, printing is just showing something on the screen. However, returning is for producing a result that you can store, combine, or compare later. In this file, we'll be writing down 3 functions, one that performs an action, one that takes an input, and one that returns a value. Let's define a function called say hello. We define a function by putting the keyword def, followed by whatever you want the function to be called, parentheses, and then pass in whatever variables that you'd like to use in your function. In this case, we don't need any variables because in this function, we're just going to be printing, so we can just leave it blank, and then be sure to add this colon here, and then in an indent under the def say hello, we're going to be writing our command. This indent is important. This basically says that this code right here will run right before this line right here. So the indentations matter. So let's print the string hello. Then we print welcome to Python. You might think that this returns hello and welcome to Python, but in reality, this function will return nothing. In this case, we have 2 print statements. So all this is going to do is just print these 2 statements. In this case, you can't use any of the values that come out of here because they're just print statements. So what if we ran this? Would this print hello and welcome to Python? Nope, absolutely nothing. That's because we haven't called the function yet. So in order to see the print hello, we would have to actually run it, and we call it like this, the function name with open parentheses. We would call it like this with the function name and whatever arguments that you want to pass in. In this case, it's none, so we can just call it like this. Be sure that you have the parentheses. Otherwise, If you just had this, it would do nothing because you're not actually calling anything. But now, if you add the parentheses, this actually will run the function. Now, let's define a function called greet. In here, we want to have it greet us by our name. So in this case, we're going to define it like this, define greet. And then instead of passing in nothing, we want to make sure that this function greets us by our name. So we can pass in a name variable, and then we can have it print the string hello, and then we can have it be name. And in this case right here, we pass in a string variable called name, and then we can concatenate this to the hello string. Oops. So we can call it like so. And now we can pass in a string variable, say Kelvin. And so what this will do is it'll take the Kelvin and concatenate this to the hello. And if you print this, we see the correct output. Again, this doesn't return anything. All it's doing is printing. Now, what if we actually wanted it to return something? Let's do a simple mathematical function. Let's do def add. And in this scenario, we want to add A and B. And in this case, right, we'll pass in an integer A, or a float A, or a B integer, or a float. And then we can simply have it return A plus B. And we can call it like this. We'll pass in 5, and then we pass in a 9. We can separate the variables with a comma right here, and then this will return 14. But of course, this doesn't do anything because this isn't a print function. All this is doing is it's running the add function 5 plus 9, but we're not actually doing anything with this function, so nothing is printed. Now, what if we added a print statement right here? Now we're actually doing something with this value, because what this will basically evaluate to is A plus B, or 14. So this is all this is saying is print 14. If there's one thing that you remember from this section, be sure to remember that a function that prints is not the same as a function that returns. If you need a value for it later, you have to return it. If you only print it, you can't reuse it. If a function does not explicitly return something, it returns a value of none by default. So in greet, right here, even though it prints hello name, this will evaluate to a value of none. Let's move on to the second exercise file. Let's call it 8-2-py.py. In this section, I want to cover scope, defaults, and calling style. The goal here is to learn what variables exist where, how to make parameters optional with defaults, and how to make function calls more readable with keyword arguments. These are all things you will see constantly in real production code. Let's cover scope first. Variables created inside a function are local to that function, meaning they don't leak out of the function. This is good because it prevents accidental conflicts, but it also means if you want a value outside the function, you have to return it. The second is default parameters. Defaults let you give a parameter a standard value, so you don't have to pass it every time. This is a realistic feature you'll use whenever most calls share a common value. The third is keyword arguments. Keyword arguments let you call a function by naming the parameters. This makes calls easier to read and prevents you from mixing up the order. We'll use a simple example for all three concepts. Let's create a function called def compute total. And what this will do is it'll take a price and a tax rate variable, and it'll return the total. Let's give tax rate a default of 0.0625. So we can define it something like this, a float of 0.0625. And this is basically the default parameter here. So if you don't pass in tax rate, it automatically defaults to 0.0625. Of course, you can also pass in your own tax rate variable and have your tax rate be something like 100%, 200%, or 0%. But if you don't pass in anything, then this automatically defaults to 0.0625. Now, we'll define a variable called tax, which is equal to price times the tax rate. Now, let's notice that tax is a local variable, meaning this variable is only defined within the compute total function right here. So what if we wanted to print tax outside of the function? You'll see that outside of the function, tax is not defined, even though tax is defined right here. This is because, or in this case, tax is in only the scope of the function, but it's not in the global scope. So the print value in the global scope doesn't recognize the variable tax. Now, we can have it recognize the tax variable by putting it inside the function, like so. And you can see that it's no longer throwing an error because now that the print is inside the local scope, it can get the tax variable from right here. We'll do the same thing with a total. Total is equal to price plus tax. And then we'll have it return total. Let's test the default tax rate. So we can pass in print, compute, total, and we'll have it be 100. And this should give us $106.25 because the tax rate, we don't pass in a tax rate variable right here, so it automatically defaults to this tax rate right here. And we can print this 106.25. And then let's test if we wanted to override this tax rate right here. So we had compute total. And let's say that we want a 100% tax rate. Since we're using decimals, this will evaluate to 1. 100% tax rate is 1. And then we'll see that this tax, the total, is going to be 200. Now, we can also use our keyword arguments, compute total, and then we can specifically have it be total, or price, is specifically equal to 100, and then we can have the tax rate is equal to 0.10 or 0.1, and we can have the tax rate be 0.1. This needs to go in here. And now this should give us 110. Oops, got it unexpected. Oops, this should be tax rate. See, it has to match exactly 110. The big takeaway from this section is that functions will create a clean boundary for you. Everything inside will stay inside unless you return it specifically. Let's move on to our third exercise file. Let's create a file called 8-3. Oops. 8-3.py. And in this section, we want to cover functions that make decisions and protect your code. In real programs, functions are often used to enforce rules and keep the rest of your code safe. What does that mean? Instead of sprinkling checks everywhere, you put the logic in one place. This is especially important for beginner code because it prevents errors and makes your program predictable. In this section, we're going to build two small validation style functions. The first returns a Boolean so you can use it in conditionals. The second will return none when it can't produce a valid result, which is a pattern you've already seen with missing values earlier in the course. Let's define a function called isPassing. And in this scenario, or in this function, we're going to be taking a parameter called score. And we only pass if the score is greater than or equal to 60. So we can do something as simple as this. Score is greater than or equal to 60, and this evaluates to a Boolean. So if we pass in a 70, this will return true. If we pass in a 50, then this will give us a false. Or this whole function evaluates to a Boolean value. We can use this return value because we can directly plug it into if-else logic later. Let's verify that this function works, is passing. So if we pass in a 60, although it's on the cusp, it should pass. True. But if we pass in a 50, or even just a 59, not 590, we'll get false. Let's define a function called safe divide. And this function is going to help us prevent unsafe division. So if b is equal to 0, as in you can't divide by 0, we return none. And then we can print if b is equal to 0, then we return none. Because if right here, we can't divide a by 0. So we can have it print an error. And if this check doesn't, and if b is not equal to 0, then we can do our division safely. A divided by b. We can test this. Print safe divide, pass in 10 and 2. This should give us 5. It goes 10 and 2, replace the variables b and a in here, passes this check, a divided by b. Now, if we pass in 10 and then a 0, we can't divide 10 by 0, so this should give us none. Because it goes into this conditional and it returns before it ever reaches this. The point here is that functions don't kind of just compute. They also will enforce rules and handle your edge cases in one place, so the rest of your program will stay clean. Also, one thing I wanted to mention, or one thing that's really important, is you can only return once in a function. So in this case right here, this is the perfect example. Because if b is equal to 0, we go here and we return none first. So that means the function will only ever return none. It won't return two values because we'll never ever reach here. Because as soon as it hits a return, we're out of the function. And none of the code after that matters. Let's move on to our next section. Let's call this a-4.py. In this section, I want to cover using helper functions with loops and lists. This is where functions kind of start feeling like a tool that you can actually use. The goal here is to show a real pattern. When you have a loop doing work on many items, the loop should stay simple. The how do we process one item logic should simply go into a helper function. What does that mean? Let's define a function called cleanName. And what this will do right here is take in a name string, and it'll help us clean the string. So we pass in name, and then we strip any trailing white spaces, trailing or preceding white spaces, and we'll keep it lower. And we'll keep it lowercase. So if we pass in, this should be cleanName. Again, the function name has to match exactly, or the program's not going to know what you want to do. And we can pass in Calvin, have a bunch of extra stuff here, and let's print and see what this gives us. if we've done it correctly, this will just give us Kelvin, all lowercase. And we see that we've done it correctly. Now, what if we had a list of raw names? Say we had this string right here, this messy Kelvin string right here, and then we had oops, don't do that. We have Ava, well, uppercase, and we'll have John with a single space, and we can have Paul. Now, what if we wanted to take the raw names and process every single item in the list with clean name? Rather than writing clean name out 4 different times, what we can do is simply loop through raw names and apply the clean name function on every single value in the list. So we can do for name in raw names, we can apply let's create a new list for a resulting list, or after we've cleaned all the values right here, and we can iterate through raw names, apply cleaned names function on each one. So we're going to append every single value that we get from this loop into clean names, and we pass in clean name. And what this will do is, for every value in raw names, it'll apply this line of code until we run out of values in the list. And let's see what cleaned names looks like afterwards. So after we run this for loop right here, we apply this function, this line of code, on every single value in raw names, and then we append it to cleaned names. And as you can see, we get Kelvin, Ava, John, Paul, with the clean name function applied on every single one. Now, it may not seem like all that much to write down clean name 4 different times for each one of these values. What happens if our raw names list is, say, 50 values long? In that case, right, we would have 50 lines of code compared to 2 lines of code, because this will just iterate through every single one of these values. We can also do the same thing with a def count greater than function that takes in numbers and threshold. Is a little bit more complicated of a function. We have count is equal to 0 for n in numbers. If n is greater than threshold, then our count is equal to count plus 1. And then we'll return count. Say we had a nums list with 2, 7, 4, 9, 10, and 3. Now we can call the function count greater than, and then we pass in our nums list, and then we can pass in a threshold of 5. And in this case, since it takes in the whole list here and it applies the threshold comparison, we can get 3, because we know we have 3 values in here that are higher than the threshold that we set of 5, that being 9, 10, and 7. Now, if we wanted to do the same thing, and we pass in our list the same way, and say we had a threshold of 9. In this case, we'll expect only 1. And that's what we get. Since we've gone long enough, I think I will make this into 2 parts. Be sure to check out part 2 coming soon. There's a lot more to cover in functions, and I don't want to rush covering functions because, again, this is the baseline or foundation for all software engineers. You have to understand this, so I don't want to rush it. So be sure to hit the bell notification to get notified of the next part coming out. As usual, we'll do git add lesson 8, and then we'll commit this. And then we'll do git push. And now this is saved to our course repository. Thanks for watching, and I'll see you guys in part 2 of lesson 8. Hey everybody, my name is Calvin, and welcome back to episode 9 of my Learn Python series. Today, we'll be covering part 2 of functions. The last functions video covered the basics of functions, that being defining and calling them, parameters, return values, defaults, keyword arguments, and using helper functions. In this video, I want to cover the extra function features that you'll use once your scripts get a little bigger, such as early returns, returning multiple values, flexible arguments, nested functions, mutability, docstrings, and importing helpers. This is a continuation of part 1. Be sure to check it out before you check out this video. The link is in the top right corner, and as always, the course repository will be linked in the description, and I always recommend watching the earlier episodes before this for the best learning experience. Before we jump into the lesson for today, I have an announcement I'd love to make. Have you ever wondered how the biggest companies in the world organize, sort, and analyze their data? It's from the work of data engineers. Data engineering is the backbone of modern analytics, business intelligence, and machine learning. Data engineers in the US earn around an average of $130,000 per year, with some even making over $200,000 annually. Hi, my name is Calvin Lin, and I wrote this book because this is something that I wish I had when I first started out. From databases, data warehouses, and real-time data streams, this book will give you a great foundation to launchpad your data engineering career. This is Modern Data, from Ingestion to Production. Available on Amazon, Apple Books, and Barnes & Nobles, so get your copy today. Hey, welcome back. I wrote a book called Modern Data, and I'd love for you guys to check it out. The links are in the description. Let's jump into the lesson for today. Let's create a folder called Lesson 9, like we usually do. And we'll create our first exercise, 9-1.py. In this exercise, I want to cover early returns and guard clauses. The section here is about writing functions that are easy to read. A common beginner problem that a lot of people run into is nesting way too much. You end up with if statements within if statements within if statements, and it becomes harder to follow what the function is supposed to do. Creating early returns fix that. We can check the invalid cases first, and then return immediately, and then the remaining code can really just focus on the normal case. This makes the function shorter and reduces indentation, which reduces confusion. We'll write a function here that applies a discount. The function has 2 rules. Price cannot be negative, and the discount percent must be between 0 and 100. If any rule fails, we'll return a none value. If the inputs are valid, we can compute the final price. We'll call this discounted price, and it'll take in 2 parameters, price and discount percent. Our first clause is if price is less than 0, because you can't have a negative price, we'll return none. And our second case here, if discount percent is less than 0, or discount percent is greater than 100, we'll also return none. In this case, neither of these clauses would make sense within the context of a function. So the best thing we can do here is return none. Really, you can return whatever you want, but in this case, none makes the most sense here. Then we'll have our actual logic. discount amount is equal to the price times the discount percent divided by 100. And then we can return the price minus the discount amount. This clause right here is to make sure that since we'll be passing in an integer value for the discount percent and it's not going to be a percentage, if we put in 70 here, this will just equate to 70 over 100, or a 70% discount. And then we can see a couple of examples, such as 100 with a 20% discount. And here we'll expect 80, print discounted price, oops. Price 50, and with a 0% discount, that doesn't make sense. We'll do discounted price with a 50% price and a 0% discount. In this case, we'll just get 50 because there is no discount, and we can have a 0% discount. Discount price, and then we'll have a negative value for the initial price, which makes no sense, so this should return none. And have discounted price, 100, 200, which also makes no sense because you can't have a 200% discount. The highest value you can have is 100. We'll run this, and you can see that's what we get. Again, pay attention to the last two calls. We'll return none instead of just crashing. That makes the function safer to use. The caller can check for none and then decide what to do next. In this case, if we remove the guard clauses, we wouldn't crash, but we would get values that don't make sense within the context of the function. Let's move on to our next exercise. In this exercise, I want to cover returning multiple values. Sometimes, it makes sense that one function can naturally produce more than one result. In Python, you can return multiple values by separating them with commas. Python packages the return values together, and the caller can then unpack them into multiple variables. This is useful when the results are related and you don't really want to recompute anything. A common example is tax and total. Another can be min and max. And another example is a clean value plus a success flag. We'll compute tax and total in one function, then we'll pack the result into two variables. We'll call this function compute tax and total. It takes in a price variable and a tax rate that defaults to 0.0625. Again, remember here, if we don't pass in anything for the tax rate, it'll automatically default to 6.25%, but we can define this on our own. Tax is equal to the price times the tax rate. And the total is equal to price plus tax. And in this case, we want to know both tax and the total. So we can just do something as simple as return tax, comma, total. And what this will do is this function, compute tax and total, will give us both of these values in the return. And we can just extract them as variables like this. Tax, comma, total is equal to compute tax and total. Another thing to note is that these variables do not have to match what you're returning up here. So if anything, let's just do this. We'll have TX and TL, which stand for tax and total. I'll have $100. And in this case, we know that the total will be $106.25, and the tax is $6.25. So if we print the variable TX, we print the variable TL, we should get exactly that. And we see that's what we get. Again, we can do the same thing if we defined our own tax rate. So, comma, dot 1, say we had a 10% tax rate. Run this. $10 for tax and 110 total. The key detail here is the unpacking line. The TX and TL is equal to compute tax and total is the line that will assign the first return value to tax and the second return value to total. And the way you assign these are in the way that this returns. So I could do something like TL and TX here, and then the TL variable will hold the tax value, and TX will hold the total value, even though that doesn't make sense. You can see that these are flip-flopped right here. Let's move on to our next exercise, 9-3.py. The section here is about writing functions that can accept a variable number of inputs. You can see this in real code when you don't know how many values the caller will pass, or when you want to support optional configuration. There are two tools to help us do this. The first is *args, which collects extra positional arguments into a tuple-like group. You can loop through it like a list. And then we'll have keyword args, denoted like this. And what this will do is it collects extra keyword arguments into a dictionary. The keys are the parameter names, and the values are what the caller passed. First, we'll work on args with an add-all function. In this case, we'll accept any number of numbers and return the sum. We're using a loop, so you can see the logic instead of using Python's built-in sum operator. All right, we'll define a function called addAll, and what this will take in is *args. And we'll set total is equal to 0. And then for n, in the args that we passed in, well, total is equal to the total plus n, and then we'll return the total. Very simple function. And now we can pass in a variable number of inputs. So we can do something like print add all and say we had 1, 2, 3, 4, 5, 6, 7. And we'll get whatever this adds up to, which is 28. Or we can just do print add all and do 100. And since 100 plus nothing equals itself, this should give us 100. Again, this will accept a variable number of inputs. And if we had add all with nothing, we'll expect to see a 0, which makes sense as well. See how there's a variable number of inputs? 0 here, 1 here, and 7 here. Next, let's touch on keyword args. We'll accept any number of named fields and then print them. The example here is useful because it shows you what keyword arguments look like and how you can loop through it. We'll define a function called printProfile. And what this will take is *kwrgs. And then we can loop through this in like so. For key in kwargs, we'll print key is equal to keyword args key. And what this will do is it'll index the kwargs dictionary. And then we'll run printProfile. And then we'll have name is equal to Kelvin. We'll also pass in another variable called Boston. Oops. And we'll pass in a role variable as well. And we'll just set ourselves to student. And what this will do here is you'll see each key and its value printed. The key here is name, Calvin, city is Boston, and role is student. Keyword args is often used to accept optional settings like debug is equal to true, retries is equal to 3, or timeout is equal to 10, and similar other configuration parameters in Python libraries. Let's move on to our next exercise, 9-4.py. And here, I want to cover nested functions. What is a nested function? A nested function is a function that is defined within another function. It's useful when an inner function is only really meant to support one specific task. It helps keep our file cleaner because then we don't have to create extra global functions that we don't want others to call directly. Nested functions are also useful when the inner function needs access to a value from the outer function. That's how closures work. The inner function can, quote, remember values from the outer function call. We'll do a couple examples. One creates a customized checker function while the other keeps a helper function private within a larger function. Our first example is a minimum length checker. You call make min length checker 8, and it returns a function that checks whether a string has length at least 8. Let's write this function, def make min length checker, and we'll pass in a variable called min length. And then we'll have a nested function in here called check, which takes in text. See how this is indented within make min length checker? That is a nested function. And in this case, we'll return len text is greater than or equal to min length. And then simply, here, we can just return check. And what this function will do is that the return function will check whether text is at least min length characters long. We can call it like this, is long enough. Call this our variable, and we'll have it be defined as make min length checker, pass in a value of 8. And the way we can use this is we can do something like print is long enough, and we can pass in whatever string. So say hello. This will get us false because hello with a character length of 6 is not longer than 8. But what if we did the same thing for something that was longer? And this is obviously greater than 8. I'll run this, we'll get false and then true. The thing to notice here is that check uses the min length, even though the min length is defined within the outer function. Min length is defined right here, and min length is used within the check nested function. Let's have a second example to hammer this home. Our second example, we want to normalize a list of names. We'll define a clean function within a normalize names function, because clean function is only needed within the context of the outer function. So we'll have this called normalize names, and we'll pass in a list of names. And then we'll write our function called clean name. And what this will do here is it'll return the name, stripped, and lowercased. And we'll have our clean names in an empty list right here. And then for n in the list of names, we'll append the cleaned result to the list. Then we'll return our cleaned list. So let's define an example right here. So we'll have a bunch of space here, and we'll have Calvin. We'll have Ava, all uppercase, and we'll have Noah with lowercase. Now we can pass this in. And we'll get our list of cleaned normalized names. Like so. The main idea here is pretty clear. We know that normalized names is the function that we want to expose. while clean is just a helper. We have no reason for a user to use the clean name in here. Really, we want to only expose the top level function right here. Let's move on to exercise 5. In exercise 5, I want to cover mutability when passing values into functions. The section here is about what changes when you pass a value into a function. Again, you need to know this because it affects bugs and surprises in real-life scripts. Remember, lists are mutable. That means a function can modify the list, and you'll see the change outside of the function. Integers and strings, on the other hand, are not mutable. You can create new ones, but you cannot change the existing value within place. This means if you want a new integer value, you have to return it and assign it. Let's check out list mutation first. We pass a list into a function, append to it, and then the caller will see an updated list. We'll have a function called addItem, and it'll take in an items list right here, and whatever new item that you want to append. And we'll do simply items.append and append the new item. We'll define a list of names is equal to Calvin and Ava, and we want to pass in a new name, Noah. And then we'll print our list of names. And what this will do is it'll append Noah to our list of names right here. Names here is the same exact object. Remember this. This is the same object here. All we're doing is we're going to be changing the list of names by appending to it. Because the list is mutable, we can do this. And we'll print this, and we can verify that our function works. Now, what if we had integers? We'll call add1. But unless we store the return value, the original variable stays the same. Let's define a function called add1, and I'll take in a variable x, and then x is equal to x plus 1, and then we'll return x. We'll set n is equal to 10, add 1, and print n. We see that n cannot be changed here. We can call add1, but unless we store the return value, the original variable stays the same. So you might think that print n right here will give us 11, but that's not going to be the case. It'll just be 10, because integers are not mutable. So if we wanted to have 11 here, we'd have to do something like this. Set n is equal to add1, which takes in n from above. And now we have n redefined. Now, if we printed n, we'll get 11. The main point here is that with mutable objects like lists, the function can change the original object. With integers, on the other hand, you should expect to return a new value and then assign it. Let's move on to our next exercise. Here, I want to cover something that will be really important, and it's not really about coding. Here, we'll cover docstrings. Docstrings are about how you document the functions within Python. The docstring is a triple quoted string that's at the top of the function body. Tools can be used to display it, and it helps you later when you forget what your function does, because inevitably, you'll have a ton of functions. Say we wanted to write a clamp function and then include a docstring. We'll call help clamp so you can see the docstring show up. Let's write the function def clamp, takes in value, low and high, and what this will do here, this is how we define our docstring, triple quotes, and we'll document our function like so, keep value within some inclusive range. And have low and high. If value is below low, and then we return low. If value is above high, we'll return high. And otherwise, we'll return value. And then we'll write our logic. If value is less than low, we'll return low. If value is greater than high, we'll return high. And we'll resort to returning value at the end. Now, if we do this, clamp 5, 0, and 10, we'll expect our function here to return 5 because it'll clamp to 5. Print clamp, and say we had a -2, 0, and 10. We'll get 0 because our lower is 0. And we'll just have a normal example. So we'll have our high be 99 and 0, and then we'll just pass in 10. And here we'll just get 10. And then we'll also call a function called help. Let's see what this will do. We'll see that our function returns our expected values. But because we called this built-in Python help function, what this will do is it'll return us the docstring that we defined above. This is useful when we want to just reference what a function does. It doesn't make a lot of sense right now for us to call help within this small file. But what happens if you have a large code base and we're calling some random obscure function that's not really in here? What this will do is it'll automatically just give us information. So we don't have to go digging for it. You'll see this a lot. You'll see this a lot in real Python libraries. Let's move on to our next exercise, 9-py. And we'll also create a utils.py here. Here, I want to cover imports, specifically importing functions. The utils.py will hold our helper functions. We'll import them into a script file, and then we'll use them. This is normal Python project structure. Once you write multiple helper functions, we typically don't keep them all in the same file. We'll split helpers into a separate file and then import them. Let's write a function called def clean name, and it'll take in a name. And this is going to be the same logic from before, our nested function. But this is a helper function right here, and then we'll also have a compute total that we've also seen before. I'll pass in tax rate is equal to 0.0625. We'll return price times the tax rate. We've defined these two functions within our utils.py. So let's save this. And then let's go to our script file, 9-7.py. We can simply import our helper functions from utils.py by doing from utils import clean name and compute total. And we'll know that we've successfully imported it if this turns green and these turn yellow. Might be different on your code editor, but this is how it shows up on mine. And we do from, the pattern is from utils, which is the name of your file, minus the .py, and then we can just directly import our function names. So what if we changed the function name down here to utility.py? We'll skip the changes there. But now we'll see that our import utils cannot be resolved because before we were importing from a utils file, but now it's no longer called utils. If we wanted clean name and compute total here, we'd have to also change this to utility. We'll see that the error correctly resolves. And now we can use this in here. So here we'll define a raw names is equal to Helen and John. And we'll also define a cleaned list that's just empty for right now. And then from here, we want to do for n in raw names, we'll append our clean name to the cleaned list up here. The cool thing here is that we're using clean name from utility.py. We don't have to redefine it in this file. Now, let's test this. Print cleaned. And we'll also do print compute total of 100. Remember, this will give us $106.25, and this will give us our clean names. Run this. That's exactly what we get. And that does it for the concepts I wanted to cover today. As usual, we'll do our git status, git add our lesson 9, git commit. We'll have lecture 9, which is functions part 2. And we'll git push. And that does it for the exercises I wanted to cover for today. In this episode, we've covered function features that show up quickly once you stop writing tiny scripts. Again, early returns keep your logic readable. Returning multiple values let one function produce a complete result without any extra work. Args and keyword args let functions accept flexible input. Nested functions help you keep helpers local and build customized behavior, while mutability explains when a function can modify your data. We also want to know about docstrings, which are standard function documentation, and then imports are how you organize your helper functions across any files. In our next episode, I want to cover intro to object-oriented programming, things like classes and methods. Thank you guys for watching, and I'll see you guys in the next video.